Hello, my name is Amir Reza Baqarzadeh. Today I'm presenting comparing cognitive instance-based, and reinforcement learning model in an interactive task. This work tries to answer fundamental questions of learning bias in cognitive models, like how decision-making strategies in different cognitive models vary and why. To elaborate more on that, let's assume we're facing a situation where we have a set of choices that we have to choose from. Each choice has a unique feedback, we also call that reward, which is unknown to the user. As the instance-based learning studies suggest, initially the naive user will randomly choose an option, and as he chooses that option, he's going to observe a reward. Later, when he faces the same situation, they'll have an idea of the outcome of the choice they took. After enough trials, they will have an understanding of the outcome of all the choices, and they can implement a strategy to make meaningful decisions. So in this study, we will analyze the decision-making process of different cognitive models. A choice task model is a common method of analyzing the human decision-making process. We also saw an example of that in the previous slide. As we explained, a choice task consists of a set of options with different rewards. However, the distribution of rewards are unknown to the users. And we want to study if the cognitive model will learn bias, and if they do, how would they use this information. In order to limit the parameters involved in the decision making, we will limit the choices to only two, which is referred to as binary decision making. An instance of the binary choice task is the bias coin flip game. In the bias coin flip game, participants or model are asked to predict the outcome of the coin flip in each trial. The outcome is usually biased towards one of the choices, and participants and models are not informed of this bias. This bias coin flip game is inspired by Actor tutorial lesson number 6. We developed this game as a web-based application in C# and ASP.NET. The game is designed so that the head appears in 70% of the time, and the results of each trial is automatically saved for further analysis. So here's the initial interface of the game, which indicates that the game is ready to start. There are 3 clickable objects here. The first 2 represent the user's options to choose from. If they click on the head, the game assumes that they are predicting the next coin flip result to be head. If they click on the tail, the game assumes that the user's prediction of the next outcome is tail. And if they click on reset, the game environment is going to be restarted, so the result of a different user can be saved separately. Now let's say our user decides to play head, so he's going to click on the head. And as you can see, there is a feedback over here that indicates whether the prediction and the actual results match or they don't. So the prediction of head was correct this time. Let's say the next time when the user clicks on tail, the actual result was head. So we can see that there is a mismatch, and the feedback is going to be wrong, meaning that the results of the game and the choice of the user were not the same. The effect of unknown bias on decision making in a binary choice task has been studied before. However, the results are contradictory. Most studies indicate that people will either maximize the reward or match the unknown bias, but why and when the users will lean toward either of these is still unknown. For example, in year 2005, Altman and Burns indicated that people would lean towards matching the unknown bias, which is in line with what Vulcan observed in year 2000. In the year 2018, Plate et al. Indicated that younger children within the age of 3 to 5 demonstrate maximizing more than older children. Now that we know there are different types of behavior by different types of people, we need to know what models are capable of matching and maximizing to be able to model them differently. Now let us elaborate more on what we meant by maximizing and matching. Maximizing is referred to as only choosing the option with a higher probability of success, whereas matching is referred to as taking the action with the same proportion as their probability of success. For example, in our game, if we assign the probability of head appearing to 70% and probability of tail to 30%, if we choose maximizing decision-making strategy, we will only take head as it has a higher probability of success. If we choose matching decision-making strategy, we will choose head 70% of the time and the tail 30% of the time, which is the same as their probability of appearing. If we assign the reward of 1 to matching the outcome and the reward of 0 to the mismatch, the expected reward for maximizing is 0.7 times 1 plus 0.3 times 0, where the first term corresponds to instances of playing head and the second term corresponds to the plays where tail was played. The first number is the probability of success. Let me elaborate. Probability of success, and the second number is the proportion of the time we choose that choice. For example, in the maximizing strategy, we will take head 100% of the time, so the proportion of head is 1, and the probability of success is 0.7. And if we choose matching, the probability of success of head is 70%, and in 70% of the time we are choosing head. And the probability of success for tail is 30%, and in the 30% of the time we are choosing tail. As you can see, the expected reward for matching is always less than or equal to the maximizing. In order to model the decision-making process in a binary choice task, cognitive models such as ACTAR, Pibble, and deep reinforcement learning models with epsilon greedy, Thompson sampling, and Boltzmann equation are used. These models need to interact with a dynamic environment, such as the bias coin flip game. However, these models cannot interact with the environment on their own. So in order to expand their capabilities, we developed a tool called Visitor, which is the combination of vision and motor, to facilitate this interaction. Visitor simulates a user's visual attention and the use of mouse and keyboard. This tool allows cognitive models to interact with any environment while keeping the operations similar to user as close as possible, and its capabilities are expandable simply by adding new modules to the tool. In order to elaborate on how the visitor works, we have developed the animation over here. So in our bias coin flip game, the models need to know if the game is ready to be played. So they have to send a request to the visitor, and the visitor will search on the screen to see if there's any sign of the game being ready to be played. The way it works is basically it's going to look for the ready sign with a pyramid template matching algorithm. So it's going to find the ready sign, and then it's going to send the feedback to the model that yes, the game is ready to be played. In the next step, the model decides to play head. So it's going to send the request to the visitor. The visitor will move the mouse to the head button, and it's going to click on that, and a new screen is going to appear. Now the model wants to know the feedback, so it's going to send the request to the visitor. The visitor will look over the screen to find if there is any indication about if they match the results of the computer or it was a mismatch. It's going to find a match, and it's going to send the feedback to the model. And then the model needs to update itself based on the feedback it just. Here is a demo of Visitor being used alongside with ACTAR. As you can see, the model first looked for the ready visual object to make sure that the game is ready, and then after that the model is looking for the visual objects such as head and tail whenever it decides to play them, and then it's going to look for the feedbacks corresponding to them. We're going to see that in this specific trial, based on the parameters that we chose, the ACTAR is going to move towards matching the probabilities. Here are the architectures that we use to model the cognitive process of decision making. Each model has its own unique way of updating the reward function as well as a unique decision making strategy. This uniqueness will result in different behaviors and different decision making strategy. This table summarizes the reward functions and decision making strategies of each model. So as we can see here, all these models are capable of learning the bias. However, whether or not they're capable of matching and maximizing, it's different from one model to another. The only important part to explain is that Thompson sampling first matches and then moves towards maximizing. Let's first analyze the results of Akhtar and Peeble. The figures you see here, the y-axis is the proportion of the head if the line is blue, and its tail if the line is yellow, and the x-axis is basically the iteration number. As it can easily be seen here, with the right set of parameters, both Akhtar and Peeble are capable of replicating maximizing strategy, the two upper figures, as well as replicating the matching strategy, which are the figures at the bottom. Now here are the results of Epsilon Greedy and Boltzmann. As you can see here, the Epsilon Greedy is only capable of replicating the maximizing strategy. However, Boltzmann, and just like Akhtar and Peeble, is capable of replicating both maximizing and matching. Again, it needs the right set of parameters to be able to replicate each. The most different one is the Thompson sampling, which first starts to match, and then after enough trials are passed, it's gonna start moving towards the maximizing. Here we're gonna summarize our finding. First, with enough difference in reward values for success and failure, all models are capable of learning the bias. Also, all models that incorporate Boltzmann equation in their reward function and their decision-making strategies can adapt to different strategies by changing the temperature value. The higher the temperature, the more random the decision is going to be. Thompson sampling, unlike all the other models, first replicates the matching strategy and then starts to maximize, and Epsilon Greedy is simply not capable of replicating the matching strategy. To wrap up the presentation, we analyzed different models such as Akhtar, Peeble, deep reinforcement learning models with Epsilon Greedy algorithm, Boltzmann exploration, and Thompson sampling decision-making strategies. In order to do so, a web-based bias coin flip game was developed where models can predict the next coin flip result. To facilitate the interaction of models with the game environment, a tool called Visitor was developed. We showed that among all well-known architectures in decision-making, Akhtar, Peeble, and deep reinforcement learning with Boltzmann exploration are capable of imitating all decision-making strategies. The behavioral studies in this area believe people use the same set of strategies. However, which strategy is used in what situation is still a topic of conflicts, and more experiments should be done. And finally, thank you for listening. If you had any questions, please contact us with the emails shown below, and the project is available on the project's website. And up here you can see the people's interaction with the game environment using our tool Visitor. Thank you.